Good morning, you positive people. Today is the big day, the fundamental theorem of calculus. Before we start, we're going to need the books, though. We're going to go to page 318. Natalie and Sophia, can you pass them out? If Sophia's not here yet, Jack, just give her a hand. So what I want you guys to do is go to page 318, pause the video so that everyone has one, has a book, and I want you guys to read just the first page of the fundamental theorem of calculus. This is what it looks like. Um, Zach, you or Enzo read. Colin, you pick which one reads. All right. Once you guys have done reading, and you can continue the video. The idea is we've been doing two very unrelated things now. This idea of antiderivatives and derivatives, and other than having the same word in it, or the area under a curve and the tangent line problem, the fundamental theorem of calculus is what relates them. So we've talked about antiderivatives, which is finding the antiderivative function f of x. It finds what we call capital F of x, and a definite integral finds the sum of an infinitely many, infinitely small products. So this was approximating for area, and one was giving us a family of functions that were the antiderivative of the original function. And then how are these related? Because an indefinite integral and a definite integral seem to be doing two completely different things. And at the bottom of the page that you read, it turns out that this is the case, which given capital F of x is the antiderivative of little f of x, then if you want to find the definite integral from a to b of a function, and this is also area under the curve, you can just find the antiderivative, capital F, plug in b, plug in a, and subtract them. So this will give us area under a curve. So pause the video to make sure you write down the fundamental theorem of calculus, because this form is going to be used a lot. We're going to apply it so now you can actually see how we're going to use it. But this is a big deal. This idea, this left-hand side, originally we said it's a limit of a sum, which is kind of complex. And you guys did it a few times, and it wasn't easy. So this idea of doing this limit definition of the area under a curve, you had to take a sum of infinitely many rectangles, which is a very complex idea. And it turns out it can be as simple as finding the antiderivative of a function, plugging in two numbers and subtracting them. So we're going to do a couple examples, and then you guys will do some more for homework. All right, so evaluate each indefinite integral. Here I want to find the definite integral of the function 4x from x goes from 1 to 3. Okay, so the antiderivative, the definite integral from 1 to 3 of f of x is going to be capital F of b minus capital F of a. So my function is 4x. The antiderivative of 4x, we're just going to use the power rule here. So by the way, if I want to find the antiderivative of x to the n, it's x to the n plus 1 over n plus 1 plus c. So the antiderivative of 4x is going to be 4x to the second over 2. Now, with definite integrals, we're not going to need the plus c. The reason is because you'll have a plus c here, and then you have minus another plus c, and they'll just cancel out. So you're not going to need the plus c anymore. And this is a common notation. So this is the antiderivative, and we evaluate it from 1 to 3. So this 1 to 3 here is a common notation. So I found capital F of x. It's actually going to be 2x squared, because those simplifies. Now I just need to plug in 3, and I need to plug in 1. So let me just write that. So this is 2x squared from 1 to 3. So it's going to be plug in my upper limit b, which is 3. It's going to be 2 times 3 squared. So that is f of b minus f of a. I'm going to do the same thing, but plug in 1 squared, or plug in 1. So it's going to be 2 times 1 squared. So this right here is f of b minus f of a. right? So instead of having to do the limit as n goes to infinity of the sum of f of ci times delta x, we can just evaluate this, which is going to be 2 times 3 squared is 9, minus 2 times 1 squared is 2. So it's going to be 18 minus 2, which is 16. Okay? And that's it. So if I asked you to find the area under the curve, the function 4x is just going to be a straight line. So we could have done that using an area formula like we did last time. But that's it. This idea here also works for functions that aren't nice straight lines or semicircles or whatever. So this method is going to now work, and this is what we're going to use moving forward for the rest of the year. Okay. So another example, copy it down. You can pause so that you have time to copy it down. But here we go. Find the definite integral from -2 to 5 of 3x squared minus 1 with respect to x. So again, I just need to find the antiderivative, plug in my limits of integration, and subtract them. Okay. So I need to find the antiderivative of this function. So it's 3x to the second, so it's going to be 3x to the third over 3. The antiderivative of 1 is 1x. Again, we don't need the plus c. And we're going from -2 to 5. This, by the way, simplifies. So this is really just x cubed minus x from -2 to 5. And so I'm going to plug in 5. That's my f of b. So it's going to be 5 cubed minus 5. So that's f of b minus f of a. I'm going to plug in -2 now. It's going to be -2 cubed minus -2. So 5 cubed is 125 minus 5. -2 cubed is -8. The double negative is really going to be a plus 2. So this is really 120 minus -8 plus 2 is -6. So again, this is really just going to be plus 6. And Zach, if you have your calculator, what's 120 plus 6? Thank you. 126. All right. So if I graph the function 3x squared minus 1 from -2 to 5, the area under that curve is 126. Minus 1's down here. 3x squared looks something like this from -2 to 5. So the area, there's going to be a lot of area here. And the area under that curve, you're going to subtract out this area because it's negative, but all this area up here is going to come out to 126. I don't know, five's gonna, if you plug 5 into this function, 5 squared is 25 times 3, 75 minus 1. Yeah, it's going to be bigger numbers. Okay. Evaluate each definite integral. Here's another one. Copy it down. And we're just doing the same thing every time. If I want to find the definite integral of a function, I just need to find the antiderivative and plug in the endpoints and subtract them. Before I do the antiderivative of this, I have a quotient, so I need to rewrite it so there's no quotient. But this is really equivalent to 1 over x squared is just x to the -2, which we have a antiderivative rule for that. That's just going to, now it's an x to some power, so it's going to be x to the n plus 1 over n plus 1. So -2 plus 1 is -1. So it's going to be x to the -1 over -1. And we're going from 2 to 4. I'm going to rewrite it now. This is the same thing. I can bring the x to the -1 downstairs and it becomes x to the +1. And that negative is just going to keep it negative. So plug in 4, plug in 2, and we're done. So it's going to be -1 over 4 minus -1 over 2. So just plugging in the 4 where x is, and then plugging the 2 where x is. So that's my f of b minus f of a again. So we're going to have -1/4. This double negative is really going to be plus 1/2. 1/2 is the same thing as 2/4. So 2/4 minus 1/4 is 1/4. So that is the definite integral of that function from 2 to 4. Okay. New example. Take a minute to copy it down. Pause me. and unpause me. Determine the area under the curve y equals negative x squared plus 4 between negative 2 and 2, or negative 1 and 2. So here's negative 1 and here's 2. Negative x squared plus 4. It's going to start at 4. It's going to come down like this. Its intercepts are going to be 2 and negative 2. But we're only interested in the area between negative 1 and 2. So that's this region right here. This question is going to feel different to you, but they didn't ask us to do anything new. The area under the curve is what we call the definite integral. You guys did that on the homework. So you're really asked to find the definite integral from negative 1 to 2 of f of x, which in this case is negative x squared plus 4. So that's what you're asked to do, which we now have a way of doing that. You got to find the antiderivative, so it's going to be negative x to the third over 3 plus 4x. We don't need the c. And we're going from negative 1 to 2. So that'll give me the area of that purple region. So I'm just going to rewrite this as negative 1/3 x cubed. And we're going to plug in our limits of integration here. So this 2, we're going to plug that in first. That's f of b. Then we need to subtract f of a. So it's going to be negative 1/3 times x cubed plus 4 times x. But this time we're plugging in negative 1. So 2 cubed is 8, so it's going to be negative 8 over 3. And 4 times 2 is 8. Minus negative 1 cubed is negative 1. Negative 1 times negative 1/3 is positive 1/3. 4 times negative 1 is negative 4. You guys can finish this up on your own, but what I would do here is distribute this negative. So if you distribute the negative in, it's going to become a minus 1/3 and a plus 4, which is going to make things a little bit easier because I have negative 8/3 plus negative 1/3, which is negative 9/3. And then I have 8 plus positive 4, which is 12. And 9 divided by 3 is 3, so we're going to have negative 3 plus 12, which is just 9. So as much as you need to, rewind the video. You have to play it back to kind of see what happened. These next 3, I want you to try. I'm going to go do them as well, but pause the video. See if you can give these a try. And if you're not sure, try to look back at some examples, work with the people at your desk, and give parts A, B, and C a try. I guess my hint to you on B is rewrite the square root of x as x to some power. And the secant squared one, just look at our derivative, our antiderivative list of rules that we made in 5.1 day 2. And that one should come out quick. All right, and let's see how you guys did. So the first one, if I take this antiderivative, I'm going to get x to the third over 3 minus 3x from 1 to 2. So if I plug in 2, that's going to be, let's actually do that. So it's going to be 2 cubed over 3 minus 3 times 2. Now plug in 1, so it's going to be 1 cubed over 3 minus 2 times 1. Okay, this is 3 times 1. So x cubed over 3 minus 3 times x. Plugged in a 2, and then we plugged in a 1. Okay. So 2 cubed is 8, so that's going to be 8/3. 3 times 2 is 6, so minus 6. These parentheses are going to help for the distributing this negative part, so just get in the habit of that. Then I'm going to have 1 cubed, which is 1, so it's 1/3. 3 times 1 is 3. I'm going to do that trick again where I distribute the negative. So you can think of this as a -1. If you distribute that in, and we get a -1/3 and a +3. So 8/3 minus 1/3 is 7/3. And -6 plus 3 is -3. -3 is the same thing as 9/3. So 7/3 minus 9/3 is -2/3. So if you got -2/3, nice job. If you made a mistake with like distributing the negatives, that happens. Just got to get some more reps in, you get better at it. For part B, I'm going to rewrite this integral as 3 times x to the 1/2 from 1 to 4. So now I can use my power rule. So this is going to be, I know I'm not color coding it consistently. 3x to the, so now you got to add 1 to 1/2, which is 3/2. So x to the 3/2 over 3/2 from 1 to 4. And I'm going to rewrite this. Dividing by 3/2 is the same thing as multiplying by 2/3. So it's going to be really 2/3 times 3 x to the 3/2 from 1 to 4. And that 3 kills off that 3. So it's really just 2x to the 3/2 from 1 to 4. So if I plug in 4, it's going to be 2 times 4 to the 3/2. That's like the f of b minus f of a. I got to plug in 1, so it's 2 times 1 to the 3/2. When you see fractional exponents, you can just put in the calculator, but these ones actually aren't that bad. So 4 to the 3/2. So first I can do the root part. The 2 means take the square root of it, and then the 3 means cube it. So the square root of 4 is 2. 2 cubed is 8. So this is really 2 times 8, which is 16. And 1 to the 3/2 is just 1, so 2 times 1 is 2. So 16 minus 2. Zach, if you have a calculator, help us out. Good, thank you, that's 14. All right. And the last one, let's see if anyone got this guy. When you take the antiderivative of secant squared, that's just tangent x. So that's on our chart. From 0 to pi over 4. So it's going to be tangent of pi over 4 minus tangent of 0. You could actually plug these ones in the calculator. If you remember tangent of pi over 4 in the unit circle, that's the pi over 4 coordinate is root 2 over 2, root 2 over 2. So if I rewrote tangent as sine over cosine, sine of pi over 4 divided by cosine of pi over 4, that's just root 2 over 2 divided by root 2 over 2, and a number divided by itself is 1. I mean, it's a 45-degree angle. Opposite over adjacent is going to just be 1. So if you memorize that one, great. If not, you could figure it out or put in the calculator. Tangent is 0. You can plug it in the calculator. It's just 0. Or you can put sine of 0 over cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. 0 divided by 1. And so check that in the calculator for me. We should get 0. And so 1 minus 0 is 1. Okay. And that's it for our first day of the fundamental theorem of calculus. There's a lot that there's a lot of work to get to this point, and there's a lot of work that comes from this point on. But what I want now is just us to be able to evaluate these definite integrals, and we're doing so with the fundamental theorem of calculus. So any questions, write them down, ask me next time, and then the homework assignment's getting passed out now. As some people say in some hoods, shalom.